Anybody have any questions about the test or homework problems or anything we've been doing? Okay, so what are we in the middle of right now? What have we been working on? Don't look at your notes, that's cheating. 2D kinematics, yeah. And what does kinematics mean? Oh, and these are of particles. What does kinematics mean?
Motion.
Yeah, it's related. So kinematics means we're still just describing motion. We're not talking about causes of motion yet. And so that means we're just dealing with relationships between time, position, velocity, and acceleration. And what is a particle? A particle is an object that we're treating as having no length dimension. No length. And so because it has no length, it has no orientation. And we've been talking about the constant acceleration equations. There's two more topics that we need to cover in 2D kinematics of a particle. That's relative motion. That's just a vector version of what we've done before. So those concepts are very similar to relative motion along a line. And then the second one is a new thing, circular motion. Obviously, in motion along a line, there's no equivalent to circular motion. You need to be able to turn for circular motion. Okay, so relative motion. If an object's motion is measured in two different coordinate systems, and these two different coordinate systems have to have the same axis orientation. They just have different origin locations. You can represent the location of that object in both coordinate systems. And okay, so you can measure the object's location separately in each coordinate system. And now you can make sense out of the relative motion equations if you think of, so let's say that this is our coordinate system A. and this is our coordinate system B. And let's say this is our particle P, our object. Okay. Then this vector, using the relative motion notation, is the position vector of P relative to A, represented in that A coordinate system. This is the position vector of P relative to B. Those are both vectors. This is the position vector of B relative to A. And then this relative motion equation, the position one, so the position relative motion equation is just vector addition. You can see that, by the rules of vector addition, this position of P relative to A is equal to the position of B relative to A plus the position of P relative to B. You see that? Because the tail of this one is at the head of this one, and then the resultant goes from the free tail to the free head. And so the equation you get is the position of P relative to A is equal to the position of P relative to B plus the position of B relative to A. It's identical to the 1D version. It still follows that same rule of the fraction multiplication has to work out. Remember that? But we just have vectors now. And if you take the derivatives of everything, you get the velocity relationship and the acceleration relationship. So the velocity relative motion equation says velocity of P relative to A is equal to the velocity of P relative to B plus the velocity of B relative to A. And the acceleration one says the acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. Any questions about that yet? Okay, so here's an example of how to use this. So let's say you have this cart on wheels. And it has a little launcher that's capable of launching something into the air at 4 meters per second. And let's say it's launched from a height of 0.2 meters above the ground. So let's say the cart is moving 3 meters per second this way. When the ball is launched. how far away from the launch point horizontally will the ball hit the ground? Well, if we think of this as a constant acceleration problem, a free fall problem, we can think of our origin right beneath where it's launched. Okay, and I'm going to call that coordinate system the ground. That's the coordinate system G. That's the one we want to do all our calculations in. Let's think about what we know and what we want. Do we know the acceleration of the ball?
Yeah.
Yep, it's free fall. Do we know the initial position of the ball? Yep. That's 0x 0.2 y. Do we know anything about the final position? We know one thing, because it's hitting the ground. So we know that Pfy is equal to 0. Do we know the initial velocity of the ball?
4 meters per second.
So that's where we're going to use the relative motion equation. So we still have to figure this out. Final velocity, we don't know. We're trying to find Pfx. We're not going to be able to find that in one step. So first we're going to have to find Pf and then use that to find Pfx. So now we need to find this initial velocity. So to find that initial velocity, we know that the velocity of the ball relative to the ground is equal to the velocity of the ball relative to the cart plus the velocity of the cart relative to the ground. What's the velocity of the ball relative to the cart? If you had a video camera on the cart, what would the velocity of the ball be when it's launched?
4 meters per second.
Yep, that would be the 4 meters per second straight up. Okay, someone riding with the cart wouldn't see the ball moving horizontally; they just see it shoot straight up. Okay. So this would be 0, 4. And what's the velocity of the cart relative to the ground?
3 meters per second.
Yep. In what direction?
Right.
To the right. And so if we use,
Positive,
yeah, positive x. So 3, 0. And so the velocity of b relative to the ground is equal to 3, 4. Any questions about that yet? Okay, so now we can use this as our initial velocity. And to find time final, we can use PFY is equal to P0Y plus V0Y TF plus 1/2 AY TF squared. So PFY is 0, P0Y is 0.2, V0Y is 4, minus 4.905 TF squared. Use the quadratic formula, that's C, B, A, and you get time final is equal to, you get a -1, so it's not going to be that, and you get a +1 that's 0.863 seconds. And now you can plug that into the x equation that says Pfx is equal to P0x plus V0x Tf plus 1/2 AX Tf squared. In a free fall problem, what's the horizontal acceleration? 0. So this term goes away. And you just get that Pfx is equal to 0 plus 3 times 0.863. So Pfx is equal to 0.59. Any questions about that? Okay, here's one for you to do. So let's say there's this raging river. The current's going that way. It's 50 meters across. And the river's velocity is 5 meters per second. And here's the swimmer standing on the side. Those are his feet and his shoulders, you know, bird's eye view. And the swimmer can swim. No. 4 meters per second. But like we said before, I think I used that number before. That's way too fast. No one can do that. But if the swimmer aims straight across the river, how far downriver is he when he gets across? One thing that I noticed looking at your homeworks was especially, like overall, everybody needs to show more steps. Not everybody, overall. People are skipping too many steps in their work. I need to be able to follow what you're doing, and it's going to pay off later when problems get more complicated for you, and it's always going to pay off when people are grading your stuff, so it's a habit you should get into. But I saw that especially on the relative motion equations, people would just sort of try to reason their way through it, and a lot of times you could, so I understand why you're doing that. But when these problems get more complicated again, you're not going to be able to do that. And so you need to write down that relative motion equation, okay? That's an important step of doing these relative motion problems, okay? So go up to the board, work on this problem, and be sure to write out the relative motion equation as you do it. Okay. So now do this problem again, but the swimmer aims let's say this way at 60 degrees. Okay. Okay, go. The last thing that we need to talk about for 2D kinematics is circular motion. And we're going to break this up into two different categories. The first one is called uniform circular motion. And that's circular motion where the speed doesn't change. Speed stays constant. Does the velocity stay constant? No. Why not? It's turning. It's changing directions. Yeah. And then the second one is non-uniform circular motion, and that's where the speed is changing. And the best way to think about circular motion, the best way to make sense of it is the way that we've been doing in lab, where you think about an object's path, and then you think about the direction of the velocity, the direction of the part of the acceleration parallel to the velocity, and the part perpendicular. Remember doing all that? So the velocity vector is tangent to the path. In the direction of motion. There's a part of the acceleration that's parallel to the velocity. If the object's speeding up, then A parallel is in the same direction as V. And if it's slowing down, A parallel is opposite V. In circular motion, A parallel is called the tangential acceleration. And I'll write it as A sub, I think I'll do it as A sub tan. Okay, so we're going to keep talking about it in a lot of cases where we call this A parallel. We call the other one A perpendicular. But when we're in circular motion, they have their own names. Tangential acceleration, and the other one is going to be called the centripetal acceleration, the perpendicular. And then A perpendicular is, perpendicular to the velocity vector. In this case, you can think of it as in the direction of the turn. That's always true. In circular motion, this always points towards the center of the circle. And in circular motion, this one is called the centripetal acceleration. A-C-E-N-T, I guess. Centripetal means towards the center. When you're on like roller coasters and stuff, the thing that makes you feel funny is accelerations. And so this centripetal acceleration is what makes you feel funny when you're on a ride like, the Enterprise at Valley Fair, where you're just going around and forget about the part where it tips up. You think about before it starts tipping up, you're just going in a big circle really fast. And the thing that makes you feel funny in that is all centripetal acceleration. It's the part of the acceleration that's making you turn. Okay. So let's think through some of this stuff. So there's a circle. Let's say that objects are moving this direction. And let's say there's the point A and there's the point B. So first, if an object at A is speeding up, what's the acceleration? Okay, so to think through this, what direction is the velocity vector at A? It's a two-letter word. Yes. Okay, so there's the velocity vector. If it's speeding up, what direction is the part that's parallel to that? Up. And instead of A parallel, since this is circular motion, I'm going to call this A tangential. The direction of the part of the acceleration that's perpendicular is always straight towards the center. And so if you add those two up, you get a total acceleration that's somewhere in that direction. Okay. Any questions about that one? Now for B, if the object's speed is constant, what's the acceleration vector? It's going this way. So what's the velocity? Up. What's the part parallel to the velocity? Trick question. There is none because it's not changing speed. The part perpendicular is toward the center. That's the centripetal. And so what's the total acceleration? How do we get that? It's just the same as this because there's no other part of the acceleration. So that's equal to A. And then for part C, if it's slowing down, what's the acceleration? What's the direction of the velocity?
Down. I mean, up.
Up, right. So that one doesn't change. So what's the direction, though, of the tangential acceleration? That's the one that's down. And the centripetal acceleration? Toward the center, that never changes. And so the total is this. Any questions about that? Let's go back up to the board and do the same thing, those same three questions for B, okay? So D, E, and F do the same thing for point B at the bottom. That's true. Okay. And so that is all you need to know about directions with circular motion. The rest of what we're going to be doing is figuring out magnitudes. Okay. And in order to do that, before we can calculate the magnitude of the centripetal and tangential acceleration, I need to define a couple of new things. Angular position, angular velocity, and angular, what do you think?
Acceleration.
Yes. Very good. Okay, so first, the angular position. I'll call that theta. What? Oh, yeah. I was getting too excited about angular position. Okay, so here's angular position. So an object's moving in a circular motion, and at a single instant, say this is the object, the angular position is, if you think of like a reference line along the positive x-axis, and then draw a line between the center and where the object is, this counterclockwise angle is the angular position. Okay, you're used to that idea from like the unit circle and stuff. No, you don't.
Here's the word unit circle.
The units for this have to be in radians. And notice this is for a single instant. But you could represent the angular position as a function of time. Function of time, where theta is, theta of t. Now the next one is the angular velocity. We're going to represent that with lowercase omega, the Greek letter omega, like a roundy W. And omega is a function of time. Well, what would you guess, if you had to guess, you had to, what would you guess is the relationship between angular velocity and angular position? With respect to what? Time. Yep. So that's an important thing to, don't just think of velocity and position and acceleration as related by derivatives. They have to be derivatives with respect to time. If you took the derivative of the position, or say the derivative of the velocity with respect to x, you don't get the acceleration. Okay? So this is equal to the time derivative of angular position. The units of angular velocity are radians over time. And so the SI units are radians per second. And notice that the sine of omega gives us the instantaneous direction of motion around the circle. Positive omega means it's moving counterclockwise. And negative omega means it's moving clockwise. One thing to notice is you can always figure out the direction of the translational velocity, v, if you know the direction, the sign of omega. We're not using that as a vector, and vice versa. If you know the sign, if you know the direction of v, you can also figure out the sign of omega. Like for example, if an object has a velocity vector like that, is omega going clockwise or counterclockwise? Yep. So omega is positive. And second, if omega is negative, and we're looking at the point there, what direction is the velocity vector? Up. Any questions about that? The last one we have to define is angular acceleration. We're going to use the Greek letter alpha, goldfish. And the angular acceleration as a function of time, if you had to guess what the mathematical definition of angular acceleration was, what would you guess? Yep, time derivative of omega. And that means that it's a second time derivative of theta. The units for angular acceleration are radians over time squared. And so the SI units are radians per second squared. And there's a familiar meaning to the signs of angular acceleration and angular velocity. So notice that what would you guess would be the requirement for alpha and omega if an object is speeding up? Yep, that's right. So if an object is speeding up, omega and alpha have the same sign. And if an object is slowing down, then omega and alpha have opposite signs. And what if it's staying the same speed? That's right, no alpha. Alpha equals 0. So based on those definitions, we can use theta, omega, and alpha to give expressions for the magnitudes of velocity, tangential acceleration, and centripetal acceleration. So first, the speed, which is the magnitude of the velocity, is equal to the absolute value of r times omega, where r is the radius of the circle, and omega is the angular velocity. So how do you go from the speed to the velocity? Bless you. How do you go from the speed to the velocity? Well, we already talked about how you know the direction of the velocity, right? And so the velocity is just the speed in the whatever direction you know. Then the absolute value of the centripetal acceleration is equal to omega squared times r, which is also equal to v squared over r, if you do that substitution. And then the tangential acceleration is equal to r times alpha, absolute value. So once you know these magnitudes, you can get the directions with the velocity, a parallel, a perpendicular reasoning. Okay, so let me do an example. So we have an object moving in a circle. Say it's moving this way. So omega is equal to negative 20 radians per second. Alpha is equal to, let's say, positive 10 radians per second. Say the object's there. The radius of this circle is 0.1 meters. So first, what's the velocity vector? And second, what's the acceleration vector? So for part A, the speed is r times omega, absolute value. And so that's 0.1 times 20, or 2 radian, speed is meters per second. And now, looking at the picture, what's the direction of the velocity vector?
Negative. I mean, the position of the velocity vector.
Yeah, what direction? Up, left, right? Yep. Okay, so that's the velocity vector. And so if we know the speed is 2 meters per second, this is the positive y direction. So the velocity vector is equal to 0, 2. You follow that? So we're just combining that formula with the direction. And now for the acceleration, we're going to have to do that in 2 parts. So first, the absolute value of the centripetal acceleration is omega squared r. So that's 400 times 0.1 for 40 meters per second squared. And what's the direction of the centripetal acceleration? Yep, that's always towards the center. And so we know that a centripetal is towards the center, was in the positive x direction, it was to the right. So this is equal to 40, 0. And then last, the tangential acceleration is equal to r alpha, absolute value. So that's equal to 0.1 times 10 for 1 meter per second squared. What's the direction of the tangential acceleration?
Negative.
Yeah, it's down. There's a couple ways to think about that. One is to think that it has to relate to the angular acceleration the same way angular velocity and the velocity vector have to relate. So if this one's clockwise, no, this one's counterclockwise, right? The angular acceleration is that way, so the tangential acceleration is down. It works the same as with velocity and angular velocity. And the other way to think about it is, you know that it's slowing down, right? Because these two have opposite signs. And that means that this and this have to be in the opposite direction. So that's the negative y direction. So the tangential acceleration is 0, negative 1. And so then finally the total acceleration is equal to 40, 0, plus 0, negative 1. So 40, negative 1 meters per second squared. Any questions about that? So remember these, that way of thinking, we've done that for motions that aren't circular, right? That way of thinking with the parallel part and the perpendicular part of the acceleration. But these formulas only work for circular motion. The calculations of what the magnitudes are of the tangential and the centrifugal acceleration. Okay. All right, that's all.